This is Mason Haggerty with question 41 from Chapter 3 of Fundamentals of Heat and Mass Transfer, 8th edition by Bergen. So this question says, a thin electrical heater is wrapped around the outer surface of a long cylindrical tube whose inner surface is maintained at a temperature of 6 degrees Celsius. The tube wall has inner and outer radii of 24 and 78 millimeters, respectively, and a thermal conductivity of 10 watts per meter Kelvin. The thermal contact resistance between the heater and the outer surface of the tube per unit length of the tube is R prime Tc is equal to 0.01 meter Kelvin per watt. The outer surface of the heater is exposed to a fluid with T infinity equals negative 10 degrees Celsius and a convection coefficient of H equals 100 watts per meter squared Kelvin. Determine the heater power per unit length of tube required to maintain the heater at T0 equals 25 degrees Celsius. To begin, I created this sketch showing what this tube roughly looks like. Here you can see the heater in red, while the tube itself is in black, with the inner diameter marked by the thinner ring and the outer diameter by the larger, thicker ring. All relevant temperatures and the reference points are marked, including the radii and the surface temperatures. Next, let's list our assumptions. We can assume steady state. We can assume the heater's negligible thickness, though this is not particularly required for this question. We can assume constant isentropic properties. We also can assume that the rod length is significantly greater than the radius. We assume uniform heat generation in the heater, and we are neglecting radiation for this question. For this problem, we will set up a thermal circuit shown here. As you can see, our point of interest circled there is T outside, with input heat from the heater, Q. To its right, it has the resistance of the conduction into T infinity, and that is going into QB. And then on the left, it goes to the contact resistance onto the surface of the pipe, through conduction, into QA, where the temperature is held constant in the center. From conservation of energy, we know that Q is equal to QA plus QB. So basically, the heat energy leaving on the left and right side has to equal the heat coming in through the heater. So what's QA and QB? Well, QA is going to be equal to the change in temperature on the left side over the resistance of the conduction through the pipe plus the resistance that is introduced at the contact between the heater and the pipe. So putting this together, we get T outside minus T inside over the known the resistance of a conduction through a pipe, which is ln of the outer radius over the inner radius over 2 pi k. Normally this would be times L, but however, because we are solving this problem in terms of per unit length, we will be removing that term. And then this is added to the contact resistance that is given. For QB, we're going to have the change in temperature on the right side over the resistance associated with convection. So this is equal to T outside minus T infinity, because again the heat is flowing towards QB, all over 1 over H pi D, and normally this would be have an L, because again this is H times the area, and then the area on the outside of a cylinder is pi dl, but again because we're doing in terms of per unit length, that L will be dropped. So instead we end up with QB as shown here of just T outside minus T infinity over 1 over H pi D outer. So this gives us that the heat that the heater is inputting, Q, is equal to T outside minus T inside over ln of the outer radius over the inner radius over 2 pi k plus the contact resistance that's given, this term, plus T outside minus T infinity over 1 over the H given again, pi